Hello, class. So this is going to be on Newton's second law. And it's really just F equals ma. But to really prove this law, we have to prove it experimentally. We have to set up a series of experiments and prove this. I'll start out with the situation that we had before. And I'll draw a block here. Okay. And we'll just have this, I'll draw axis. Our axis is always important. And so this is going to go along an axis here. And that's going to be x. Call that x. And actually, I'll draw that. Draw that in blue. Okay. Yeah, and I'll actually do this as the center of gravity here. Actually, we can do it like that. Okay, so that's our axis and our position, and we're going to exert some force on this, and I'll do force in orange. So here's our force, and then it's going to cause some acceleration, and I'll do that in green. Acceleration this way. And it's going to have a certain mass. And so I did different colors, and that's just to differentiate them. So it's going to have a mass m, and that's because that's in red there, force F, and orange, and then green we have an acceleration. Okay, so we have to think about how we're going to measure each one of these: force, mass, and acceleration. So the easiest way, well, first we'll start with mass. And the way we do this is we just have a standard mass that we call a kilogram. And so I'll just say this is one standard mass. And so this standard mass equals 1 kilogram. Okay, and then for all other masses, so say this is like the same material, it's going to be the ratio. And that's just like putting this on a scale or a seesaw or something like that. And think of it like that, where that's one standard mass. And so this is, so many kilograms. Like that looks like it's about like 4 kilograms or something. So we just start off with a standard mass and we compare it to that. And so we'll actually use that to prove this law out because as we can see, another way to write this is F over M equals A. And the force actually causes the acceleration. We'll see that applying an equal force to two different masses will cause an acceleration proportion to their mass. And that's basically a way to solve this out. So that's how we compare our masses, just compared to a standard mass. As far as acceleration, there's different ways to do this. One way is just to time it, and we can, basically know the position, marking it off in some way. We can mark off tick marks for every meter or something like that. And then we'll have a certain amount of time. We'll start at t equals 0 seconds, and then so acceleration should be fairly easy to measure. And you can think about doing that, maybe a motion detector or a laser or you know, anything you use to measure position and time. Force is a little bit harder, and the best way to measure force is with a spring. And so I'll do that in orange, since I already have in orange. So one way to think about applying a force, so if we're pushing force from left to right, it's basically the same as pulling it this way. And if we have a force meter, I'll draw a force meter like this. So you can think about that as a force meter, and what that is it has a little spring inside. A little spring. Oh, that's not what I wanted. That's what I wanted. A little spring like that inside, and then we pull it, and you can think about it like just pulling it like that. It's like pulling a spring with a certain force that way. Certain force that way. That's the same as giving it force with a spring. So you think about a having a spring here, and I'll draw that out. Actually, I'll draw it like that. And that'll be hooked onto something. Like that. Hooked onto a wall. And so, according to Hooke's law, who is a contemporary of Newton, a physicist, the force of the spring is going to equal negative k times x, where x is the displacement. So you could think about, we'll take, so actually, we'll leave acceleration on there. You think about displacing this a certain amount. And so that's a good way to do it. So, so I just stretched the spring out, but actually we want to compress it like that. So, yeah, so actually I want to compress it. So I'll just move the axis this way. I'll move some of these tick marks over here. Okay, so yeah, so we'll compress this spring to there. And so we compress this certain amount from here to here. So that's about 3 meters or something like that. And so that we know this is going to be a proportional force for this same mass. And that's how we're going to measure the force. So we can start off with, and so K is a spring constant, and it's going to be the same, obviously, if we use the same spring. What we're going to do, the experiment we're going to set up is for 2 different masses, we're going to compress the spring the same distance and measure the accelerations. And the experimental result to prove Newton's law, the acceleration will be proportional to the mass for the same force. So this is for mass M, and this will be a standard mass. That's going to equal 1 kg for this standard mass. And so the spring constant, we're going to say the spring constant is going to be, K is also going to equal to 1. So K equals 1, that's actually newtons per meter. And then we'll actually say we just compress this 1 meter. So that would be like going from here to here. So there, this is we're going to do it first. So that would be the natural length of the spring. And then we're going to compress this 1 meter. And so it's 1 meter like that. And I can move that down like that. So that's how far we're compressing it, 1 meter, and we're going to do it for 2 different masses. So that's number 1, and so we can write that out as the force is going to be equal to 1 Newton meter for Kx times 1 meter is going to 1 meter is going to equal 1 Newton per meter times 1 meter. So that's going to equal 1 Newton is equal to that mass times A. That's 1 kilogram, so that's going to equal A, 1 kilogram. Because this is equal to 1 kilogram times A. So since that's A, that's going to be equal to that. So we can actually just say that's a standard mass. So we're going to say that's mass S. That's going to be a standard mass, and it's going to have a standard acceleration. So I can write that as okay. So then we're going to do a bigger mass. For situation number 2, it's going to be a bigger mass like this. And it's no longer going to equal that. It's going to equal some mass M. Some larger mass. We'll call that capital M. So we're going to compress that the same amount. And then that's going to have some other acceleration that, according to the law, is going to be smaller. So to write the equation out for that, that's the force number 2. So that's going to be for big M is going to equal, the distance is going to be the same. So Kx, the distance and the spring constant are going to be the same. So that's going to also be equal to 1 Newton. It's going to be equal to big M times A for the big mass. So that's going to be capital M. It's the same force, and so that's going to be equal to that ratio. So then we can make these two equal to each other. So ms, little ms times A is going to be equal to big M times A. And then we can divide those by each other, and we can just, we'll call that capital A for the second one. Actually, I'll write that as an M for the big mass there. And that's for the standard masses. So then we divide them by each other, and then we have ms over M is equal to AM over a standard. So it's going to be there. And so you can see here that